Um, today we're gonna finish chapter 3 and move on to chapter 4. And I think I'll stop here, right before structures. So the topic of this lecture was how those like array or struct, those data actually laid out in memory. That's the topic, right? And then last time, we went over how arrays are represented, and also those like accessing code to like a specific array or a specific row will be translated into assembly code, right? And then today I'm going to go over structures. Struct, if you are familiar with C. So here is an example like a structure. On your left, there is a structure called rec, and it actually has 3 fields. Integer array with 4 elements, and size, and another like a struct. It's like a typical like a linked list like a structure, right? Because it actually has 2 value fields followed by another pointer to itself, right? So it actually it actually has like pointer at the end, so that actually you can point to the next element of the same type, the same struct, right? So this is a very typical structure. So structure is represented as a block of memory. So that block actually should be big enough to hold all of its fields. And those fields are ordered according to the declaration. So if you see, the order is, the first one is array, like integer array, second one is size variable, and third one is a pointer. And that order is actually preserved when you actually, when these fields are laid out in memory. Even if, another ordering could yield more compact representation. I'm going to explain the meaning of this when I, explain the alignments. So don't worry too much about it. The basic idea is if you actually declare those like a field in a specific order, that order will be preserved inside the struct by the compiler, because compiler is responsible for generating those code, right? And compiler determines overall size and position of fields, of course, because this code will be parsed and eventually translated into assembly code by the compiler. So compiler should know what's the size and the offset for each like field within the struct. And machine level program has no understanding of the structures in the source code. It's simply just it's compiler's responsibility to translate like access to a specific field, to use a specific value of offset and so on. Okay. So here, here's the example code of accessing those this like a struct. So let's think about this integer get app function here. So this one takes 2 input arguments. The first one is the pointer to the struct R, and second one is the index value. So what it does is it actually returns the index for returns a pointer for the index, the specific element within the integer array, right? So if you let's say this index value is 2, then it will actually return the pointer for a of 2 within the struct. Okay, so that's what this function do. So it actually returns the pointer, the location of this like element, the integer array. And if you see, you can actually calculate this value, the pointer to this like specific element within the integer array by r plus, if r is the base pointer, I mean the beginning of the struct, r plus 4 times index, right? Because the integer array is the first field, so it will be placed at the top of the the struct, and then the like nth element is because individual integer value takes like 4 bytes. If you want to access, like for example, if you want to access a second element in the array, you actually have to multiply the offset. Starting address will be like +8 from the beginning of the struct, right? So that's what it computes. So if you generalize it, the a of idx, the pointer to a of idx is calculated to be R plus 4 times IDX. So, you know, it's simply, if you compile this code, the compiler actually generates this code. You know, RDI is in R, this is R, and this one this is actually holds IDX. So if you actually use this addressing, it will compute, you know, R plus IDX times 4, right? So it will be the value computed by this expression, and then that value will be stored in register RAX. Okay? So here is like a more complicated example of accessing the struct. So let's think about, you know, you actually have linked list. So actually now you actually made a linked list like this, you know, using the same struct. The struct is the same. And there's another function called setVal. Okay? So what it does is, you know, it actually receives a pointer to a specific node in the linked list. I assume everyone knows linked lists, right? If you took data structure, you know, and algorithms, it's a linked list. So, you know, it actually receives the pointer to linked list and its value. And what it does is, you know, it read the value of I for the node it's visiting. It actually first reads the value of I, the field I, this value, and then set the value of A of I to val, which was actually passed by the caller. Okay? You actually update the pointer so that actually now you move to the next node. And you repeat the process until you reach the end of the linked list. Right? It's a very simple function. And we assume, you know, RDI actually holds the value of R, and RSI register holds the value of val. So it's, you know, calling convention because we actually pass the first two arguments using RDI and RSI registers. So if you actually compile this code, it will look like this. Okay, let's take a look at the code a little bit. So here, you know, the first, like a move instruction, you know, this move SLQ is, you know, it's move instruction, but actually it does sign extension. So because you know, this one is like a 32-bit value. Because, you know, integer is actually, you know, it takes 4 bytes, right? It's like a double word in Intel's terms. So it's a 32-bit value. But we actually eventually store the value into 64-bit register, right? So we actually have to do somehow, you know, set the value of MSBs, 32 MSBs, right? Upper like a 32 bits. So in this case, we actually do like a sign extension because it's S. We do sign extension. We actually like a load, like a read like a 4 bytes from memory, and do the sign extension to make it 64 bits, and store the result into the RAX register. Okay, that's what it does. So basically, what it does, you read the value of I, read the, you know, this value of R. The field I in the current like a node, because we know that this value actually starts at offset 16, right? Compiler already knows it, right? The compiler knows the struct, you know, the layout of the struct, and then it exactly knows that, oh, this field actually starts at offset 16 from the beginning of the node, right? So it actually, because we received the beginning, like we actually received the base pointer of the struct using RDI register, we simply add 16 to it, and then this one will be the address to the field I within the node. Okay, so it actually loads the value from it, like just read like a 4 bytes, and then store the result into RAX register. So now RAX register holds the value of you know, I field within the node. And then secondly, now we set, you know, the value of RSI. So RSI is basically holds the value. ESI is just like a lower 32 bits of the RSI register. So it actually sets, you know, stores the value of the A of I to val, because ESI register actually holds the value of val, right? Because this is the second parameter here, this one. So this instruction actually execute this line of code, second one. Finally, the third line, you know, now we updates a pointer R, the current like the pointer that points to the current node to the value of next. And then value of next can be obtained by accessing the memory location RDI plus 24, because the compiler knows, again, if the base pointer is R, the next variable will start at offset 24 from the beginning, right? So compilers automatically generate this code, to load the value of next, and then copy the value to the RDI register. In this case, RDI register actually holds the value of R in the current node. And then the next two instructions do testing. So if the value is null, if the value is 0, then actually simply it exits the loop. Otherwise, it actually go back to the header of the loop. This is it's a very simple code. So surprisingly, this original C code actually had 4 lines of code, right? But this instruction actually has only 5 instructions. So that means the semantic gap between a C code and the assembly language is not that big, right? Because it took 4 lines of code in C, but it takes 5 lines of code in assembly. So it's kind of in terms of the power of expression, they are kind of not very far off from each other. But if you actually use a different ISA, let's say you use a RISC architecture. I'm going to explain more about RISC architecture in the next lecture. But let's say you actually use a different instruction set, and each instruction is less powerful than this, then actually you actually takes a lot more instructions to actually do the same thing. So in the case, because your individual instructions are less capable, less powerful, so actually it takes actually more instructions to execute to the same thing, right? That's the difference between CISC architecture and RISC architecture. So I'm going to explain CISC versus RISC in the next lecture. So. And now, let's think about alignment requirements. So let's say, whenever you actually declare a struct, there's certain a rule that must be obeyed, and one of them is an alignment requirement. So let's say, so the alignment is actually deals with how you place those fields within this a block of memory. That's kind of alignment. So here, let's say there's no alignment requirements. Then if you actually have 3 fields, let's say there's an example a struct S1, which actually has 3 fields, character, integer array, and double. Then actually you can actually just put them back to back, right? So you get the highest storage efficiency. You can simply put those fields back to back, right? That's kind of more natural a choice. So here actually you place a C, the first field, followed by the 2 integer array elements, I0 and I1, followed by V. The double field. That's kind of a natural thing you would do. In this case, you will either take 17 bytes in total, because this one actually takes one byte. This one takes 4 times 2 bytes, right? And this one takes 8 bytes, right? So if you add them up, it'll be 1 plus 8 plus 8, so it'll be 17. So if you actually put all these fields back to back, it only takes 17 bytes. But in reality, if you actually compile this code, the compiler generates place those fields in such a way that it actually takes 24 bytes. Why? What's the point? So here, if you actually see the actual generated code, the compiler will place those fields like this. The first a field starts at offset 0, okay? And then there's 3 empty bits. The next 3 bits are unused, not used. Right? And the next 2 elements, integer elements, will start at offset p plus 4. The location p plus 4, so it is followed by I0 and I1. And again, there's another a 4 byte empty field. This is empty. Empty. And the last field actually starts at offset 16, p plus 16. Okay, so eventually they actually take 24 bytes. So this one is actually called alignment because there's a certain, so generally the alignment rule is that if your primitive data type requires a k bytes, then that a field must start at a multiple of k.
So let's think about this case. For the first variable, character, this only takes like 1 byte, right? Because it takes like 1 byte, so every element in like every character element must start at an address which is like a multiple of 1, because k is 1 in this case. But you know, all addresses are basically multiple of 1. It's like trivially satisfied because because it's like byte address. So if you're primitive data type, like the first one, if it's like a 1 byte, then the starting address must be, for that field, must be a multiple of 1, which is kind of trivially satisfied because byte address is always multiple of 1, right? So this one is a very easy one. Then what about second one? So in this case, the primitive type is actually integer. So k is 4, right? So if you actually place an integer value, that value must start at an address which is multiple of 4, because k is 4 in this case. So your integer value can be placed at address either 4 or 8 or 100 or 424. Yes, 400 and so on. Yeah. 네. 아니요. 스트럭처의 시작점 기준이기도 하고, 여기에서는 근데 기본적으로 얘도 마찬가지고, 그러니까 둘 다예요. 스트럭처의 시작점 기준으로도 멀티플 오브 4여야 되고, 그다음에 그 스트럭처의 시작점도 이 경우에 멀티플 오브 4여야 돼요. 왜 그런지는 한 3슬라이드 후에 설명할게요. 근데 여기에서는 일단 기준점 얘기하신 대로 지금 설명하는 시점에서는 그 스타팅 어드레스를 기준으로, 그러니까 아니 어차피 둘 다 어차피 마찬가지니까 그냥 이 어드레스 자체가 멀티플, 전체 이 p 플러스 4라는 어드레스 자체가 멀티플 오브 4라고 생각하시면 될 것 같아요. 네. p 플러스 4라는 어드레스 자체가 멀티플 오브 4여야 되고, 사실은 얘는 멀티플 오브 8이어야 되거든요, p는. 근데 왜 그러냐면은 그러니까 얘가 멀티플 오브 8이면 얘는 당연히 p 플러스 4는 당연히 멀티플 오브 4가 되겠죠. 그렇죠? 근데 이게 왜 여기 8이 어떻게 나온 거냐면, 이 8이 나온 이유는 스트럭처 자체도 얼라이먼트가 돼야 되는 리퀘어먼트가 있는데, 스트럭처의 얼라이먼트 룰은 얘가 품고 있는 가장 큰 k 값을 갖는 필드에 그거를 가져와요. 근데 여기서 보면 이게 제일 큰 필드가 8이잖아요. 그래서 요 시작점이 8의 멀티플이어야 되고, 그다음에 거기를 기준으로 여기는 멀티플 오브 4에서 시작해야 되고, 이런 게 있는 거죠. Okay, I'm going to get to that again, like in a few slides. So so generally, so integer in the integer case, the starting address must be a multiple of 4, right? That's a requirement, alignment requirement. The last one, this one actually takes the primitive type requires 8 bytes in this case, because double actually takes 8 bytes, right? K is 8. Then this field must actually start at address which is multiple of 8, because K is 8, right? That's the alignment requirement. Then why we do this? The question is, so again, like if you summarize, the alignment requirement means if your primitive data type requires k bytes, then the address for that field must be a multiple of k. That's a requirement. Okay, it's actually required on some machines and advised on x86, 64, but in most known compilers actually abide by this rule. I mean, they actually satisfy. They follow this rule. And why we do this? Because memory is accessed by a line chunk of 4 or 8 bytes. This kind of, you'll understand this one better if you actually understood the concept of cache, but we didn't actually introduce the concept of cache. But so generally speaking, the memory space actually is divided into multiple, several fixed size chunk. Okay, and then if your memory access go across this boundary, then the access becomes very tricky. So the point is, we want to actually make sure that single memory access always fall in some a single boundary. And so generally, if it's inefficient to load and store datum that spans quad word boundaries because of caching effect. I mean, if you actually go across a cache boundary, then that actually cache block boundary is very inefficient. So that's one reason. And secondly, virtual memory, it becomes trickier if your data actually spans 2 pages. I mean, I'm going to go get to this virtual memory part in at the end of the semester. But virtual memory means basically you actually divide your entire memory space into fixed size, like 4 kilobyte chunk, and then that's called page. So then you actually you load from page from the disk, and you store this page back to disk from memory. They actually swap those pages from disk and memory. And then if actually your memory access actually spans falls somewhere between the 2 pages, then it becomes very tricky to process the request. So don't worry too much about it, but generally at a high level, you can think of it as actually your memory access go across a boundary of a fixed chunk, fixed like a block. Then actually it becomes very tricky to process. So actually that's the reason why many architectures actually requires this aligning or this requires this alignment for data access. Okay, and this compiler automatically insert gaps. This one is also called padding, by the way. Insert those gaps in the structure to ensure the correct alignment of fields. So specific case of alignment, 1 byte, there's no restriction because k is 1 in this case, right? If your primitive data type requires only 1 byte, then there's no restrictions on address, right? Because every address is basically multiple of 1. Okay? But if you actually have a short variable, that variable must actually have an address multiple of 2, because in this case the k is 2, right? So it's the multiple of 2 means that your address, the LSB, the least significant bit of your address must be 0, right? That's the same thing, right? Multiple of 2 means it's an even number. So in order for a binary number to be even, your LSB, the least significant bit, must be 0. And if k is 4, int, float, long, if you actually have 4-byte variables, that data must be, that value must be aligned at a multiple of 4, right? So the address must be either 4, 8, 12, 16, 20, 24, and so on. And that means your address must be divisible by 4, and that implies that the lowest 2 bits of address must be 0, 0. Likewise, if k is 8, then 3 LSBs must be 0. If it's 16, bytes long double, which is kind of exceptional case, but if k is 16, then your 4 LSBs must be 0. By the way, long double is kind of, I explained a little bit. When I explained this a 14-point value, there's a special Intel specific a format of a long double, which is a 16-byte 14-point, which is more precise than double precision data type. But it's not very widely used, so it's largely there for a legacy support and legacy reasons. But if you're curious. Okay, so let's go back to the alignment here. So within the structure, each we actually must satisfy each element's alignment requirement, because each field has a specific a primitive type, and then that each field must satisfy the alignment for alignment requirement for itself. And for overall structure, I mean, you come back to your question. So in terms of overall structure, let's say, what about the alignment of this entire struct? It's actually determined by the longest a field. So if let's say, each structure actually has its own alignment requirement of k, where the k is the largest alignment of alignment of any element or any field. So again, in this case, this one actually have alignment requirement of 1. This is k is 1. This is k is 2. K is 4. Then this k is 8, right? Then actually this one, the last one, actually determines the alignment requirement for the entire struct. Okay, so in this specific example, this struct actually follows the alignment rule with k, where k is 8, because k is the largest value in any of these elements it has. So, in this case, again, like k is 8 due to the double element. For double element, k is 8. So this one actually takes the largest value from any of this is like a field inside. So then the question is, can we actually get like a, what if actually we change the order of the fields? So in this case, double, integer, and car. Then the layout will become different. Like it refers starting with v, which actually takes 8 bytes, followed by 2 integer, each of which takes like 4 bytes. The last one, like character, which only takes 1 byte. Okay. And again, even in this case, the alignment requirement for the entire struct is 8 because it's determined by the largest field. In this case, the double field, right? Let's say an array of structure. Let's say you declare an array like this. Now you actually have array of like a structure. You have like 10 copies of the struct, right? Then overall structure length is multiple of k, where k is the largest element inside the struct, and these like alignment requirements must be satisfied for every element of the array, right? So let's say in this case, A actually starts from the first one actually starts from A, and second one starts from A plus 24 because this one actually entire thing actually takes 24 bytes, including the padding bytes. And the third one actually starts from A of 48, 72, and so on. And this value of A, what's the requirement for this value of A in this case? This one. Multiple of, okay, question is multiple choice because you guys are like a super master of multiple choice questions. So let's say A is multiple of 1, 2, multiple of 2, 3, multiple of 4, 4, multiple of 8, 5, none of above. What's the answer? What's the requirement for this value of A, the beginning of the pointer? One. Answer number, the choice number 1. How many of you think 1 is the correct answer? 2. 4. I mean, it's 3, like a 3. Like the 3 is like a 4. K is 4. I mean, the choice 3. Okay. 4. Okay, good. All right, that's the correct answer. So this one actually must be multiple of 8, and the following elements will automatically satisfy the alignment requirement because this one actually starts at A plus 24, which is another like a multiple of 8, right? So if you actually if this one satisfies this rule, then all the following subsequent following elements will satisfy the alignment rules recursively. Okay? Yeah. 아, 마지막 거에. 뭐 좋은 포인트인데. 근데 그렇게 하지는 않아요. 왜냐면은 이미, 그러니까 사실은 이론상은 저기 7바이트가 사용되지 않기 때문에 거기에다 뭐 어떤 밸류를 다음 예를 들면 밸류를 써도 문제는 없거든요. 근데 컴파일러가 자체적으로 스트럭트라고 하고 그냥 스트럭트하고 24바이트 블럭을 그냥 하나의 그냥 스트럭트 이 오브젝트에다 그냥 할당을 해버리면 다른 애들은 여기가 뒤에가 뭔지 이게 뒤에가 비어 있는지 실제로 유용하게 사용하게 됐는지를 알 수 있는 방법이 없어요. 그래서 그냥 일단은 얘를 한번 이렇게 얘는 이 스트럭트는 24바이트라고 그냥 하나의 그냥 스트럭트에다 이걸 할당해 버리면은 그냥 그 안에 있는 거는 뭐 다른 베리어블로 할당하고 이렇게 중첩해서 할당하고 이러진 않아요. 그래서 진짜 마지막 하나의 바이트까지 다 빼먹어야 된다 이러면은 약간 한 얘기가 말이 되긴 하거든요. 인베디드 시스템이라 진짜 막 메모리가 한 우리 보통 PC는 한 뭐 수 기가바이트 갖고 있지만 메모리가 한 뭐 64kB밖에 없는 시스템에서 지금 프로그램을 한 바이트라도 아껴가지고 세이브해서 써야 된다. 그러면은 얘기한 대로 뭔가 이 지금 중첩을 해가지고 이 패딩 들어가가지고 지금 여기 사용이 안 되고 있는 그런 바이트들도 뭔가 다른 유용한 용도로 쓰고 막 이렇게 할 필요가 있을지 모르겠지만 대개는 그냥 그렇게까지는 할 필요 없다는 거죠. 오히려 그거를 관리하고 그런 것들 다 얘가 실제로 가용한 바이트인지 아니면 가용하지 않은 바이트인지 이런 걸 다 트래킹하고 다 이런 걸 하는 복잡도가 훨씬 그런 비용이 훨씬 더 크다고 생각하는 거죠. 네. 대신 조금 더 이런 건 있어요. 그러니까 I'm gonna explain because he already mentioned the how we can make best use of this some like a fixed number of bytes. Let me explain this slide 31 first. So generally, it's like a rule of thumb. If you actually want to minimize the number of padding bits, I mean, you actually maximize the storage efficiency with the struct. The general rule of thumb is put the large data types first. That's the general rule. So here is the two, like, let's compare these two examples. They actually have the same set of fields, but in different orders, right? The first one is a character, integer, and character. This is kind of very poor layout, I mean, because, this one actually has like a, alignment requirement of k. This one actually k is 4, right? So this one actually starts at some location, like the first byte starts here, and then the next like integer must be start at a multiple of 4, right? So you just discard next 3 bits and starts the next field at like a +4, right? And then you actually have like another followed by like another character value, and then you again waste like 3 bytes. But if you actually place this like largest like data field, I mean the largest data field first, generally that actually minimizes the waste. So if in this case, integer comes first, followed by 2 characters, so that in this case, these 2 characters can be placed in the same word, right? So actually it actually saves some space, and this one actually takes 12 bytes, and this one takes like 8 bytes. So general rule of thumb is put large data types first in the struct if you really want to save the space. 없죠. 그렇죠. 그렇지. 왜냐하면은 어떤 경우가 있을 수 있냐면은 그렇게 하면은 예를 들면 어떤 문제가 있냐면은 스토리지 에피션시는 좋아지겠죠. 어차피 그냥 예를 들면은 유저가 사실은 C 같은 랭귀지에서는 좀 안 되고요. 자바나 좀 더 상위 레벨 언어에서는 돼요. 그렇게 하는 게. 왜냐하면은 C에서는 이게 안 되는 이유가 뭐냐면 C는 그 유저가 맘대로 포인터를 어리스매틱을 하게 허용을 하거든요. 그럼 예를 들면은 내가 스트럭처를 허용한 다음에 프로그래머가 나는 이걸 나 레이아웃을 다 잘 이해하고 있으니까 나는 이렇게 그냥 타입 그 필드의 이름으로 액세스하지 않고 내가 그냥 막 매뉴얼하게 그냥 포인터 어리스매틱을 해가지고 특정한 필드를 오버라이트하고 막 이럴 수 있잖아요. 근데 그렇게 한다는 가정은 지금 그 오더가 지금 픽스돼 있다는 가정하에 그렇게 하는 건데, 근데 만약 오더가 픽스돼 있지 않고 컴파일러가 막 이거를 맘대로 바꿔가지고 레이아웃을 바꿔버리면 그렇게 막 유저가 맘대로 포인터 어리스매틱을 통해가지고 액세스하는 필드 액세스들이 다 브로큰 되잖아요. 그렇게 C라서 안 되는 거고요. 근데 만약에 자바 같은 랭귀지 쓰면 어떻게 될까요? 자바나 뭐 파이썬 이런 걸 쓰면은 얘네들은 포인터 어리스매틱을 허용하지 않아요. 그냥 무조건 액세스하려고 그러면 무조건 필드 이름으로 액세스를 해야 되지 포인터 어리스매틱 허용하지 않기 때문에 그런 경우에는 사실은 내부적으로 이 레이아웃을 바꿔서 옵티마이즈를 하는 게 좋은 초이스일 수 있죠. 근데 이 경우는 아니고, 이 경우는 왜냐면 아까도 얘기했지만 프로그래머가 나는 저기 C라는 이걸 쓰지 않고 그냥 시작하는 포인터에서 그냥 5번째 엘리먼트가 C라고 그냥 가정하고 뭐 쓰겠다. 이렇게 해가지고 하여튼 뭐 포인터 어리스매틱 해가지고 막 맘대로 바꿀 수 있잖아요. 근데 그런 프로그램도 원래는 제대로 컴파일러가 제대로 동작할 수 있도록 원래는 개런티 해줘야 되니까. 그래서 뭐 좋은 아이디어일 수 있는데 아마도 그런 옵티마이제이션 할 건데 컴파일러가 그런 옵티마이제이션 하긴 할 건데 C에서는 아니에요. C에서는 아니고 다른 랭귀지에서는 할 수도 있어요. 타입을 I로 바꾸면 I가 2개 있어요, 그러면? I를 어떻게 바꾼다는 거죠? 여기 이걸 이렇게 I로 바꾼다고요? 이거를? 여기 이렇게? 그러면 I가 2개면 컴파일러 에러가 나죠. 똑같은 필드가 됐다. 이런 에러가 나오겠죠. 실제로 아예 그냥 컴파일이 안 되겠죠. 근데 그게 질문의 내용이 맞아요? 뭐를 어떻게 하면? 뭐를 어떻게 하는지 먼저 설명해야지. 뭐를 어떻게 하면 돼요? 이게 아니고 뭐를 어떻게 하면? 아니 뭐를 어떻게 하면은 뭐를 어떻게 하면은 해야 이걸 어떻게 이용하는지를 그 앞부분을 먼저 얘기해야지. 뒷부분 전에. 그러니까 뭐를 어떻게 하면은 이렇게 이걸 사용하나요라고 물어봐야죠. 네. 네. 그러면은 여기가 되겠죠? 구조체 자체를 새로 짜는지 바로 이용하는지. 만약에 이걸 어떤 새로운 구조체를 만약에 적용을 하면은 디파인 한다고 하면은 S5라고 칩시다. S6라고 칩시다. 그래서 여기에 캐릭터 I, 캐릭터 C, int I. 그다음에 이거 쇼트로 바꾼다고요? 쇼트 D 이렇게 하면은 이거는 다른 스트럭트인데 S4랑은 다른 스트럭트죠. 그러니까 얘도 그냥 독립적으로 존재하는 스트럭트고 얘도 독립적으로 존재하는 스트럭트니까 둘 사이 아무 관계가 없죠. 얘는 또 다른 이런 걸 만들겠죠. 이렇게 해가지고 여기에 C 패딩 들어가고 여기 I 들어가고 여기 두 개 여기짜리 여기 이렇게 이런 걸 또 다시 만들겠죠. 뭔가 만족스럽지 않은 것 같은데 하여튼 네, 지금 아직 질문에 이걸 잘 네. 네. 어떻게 수정을 해요? 그러니까 수정을 한다는 게 무슨 의미죠? 그러니까 구조체를 수정한다는 게 그러니까 값을 수정하는 게 아니라 값을 오버라이트하는 게 아니라 구조체를 수정한다는 게 무슨 의미예요? 그러면 컴파일을 새로 하니까 예전에 있던 타입은 없어지겠죠. S4라는 타입, 그게 리디파인 되는 거잖아요. 새로운 타입 자체가. 제가 질문의 요지를 잘 이해를 못하는 것 같은데 하여튼 끝나고 나서 다시 물어보세요. 혹시 만약에 좀 잘못 이해가 안 됐으면. 예. 그래서 so let's go back to slide 30. So how we can access array elements? Okay. So here, this one actually shows the array of structs. Now we actually have 10 like structs, like struct elements, and each actually has 3 fields. So we know that actually compiler knows that individual like a struct, like single like struct takes like 12 bytes, because so actually if you want to access like this element, let's say you actually takes one like a parameter, like one argument, which actually points to the exact index for the struct, then it actually returns a value of j in this like struct in array A. Let's say that's the function. Then we actually have to first compute the starting address of this A of I index, right? So in this case, because the compiler already knows that one instance of this like a struct takes 12 bytes, so you can, this address for this A of IDX is simply you can compute it as the base address like A plus 12 times IDX, right? And this also compiler knows that this field J actually is at offset 8 within the structure. So the address for this like return value is A plus 12 times IDX plus 8. That's the location of the value we want to access, right? So if you actually compile it, it first actually computes the value of 3 times IDX and actually use this like load instruction with this complex addressing, like this scaled addressing. So if you compute this one, it'll be like A plus 8 plus, so RAX is already like a 3 IDX, so it will be like 12 times IDX, right? So that's the like location, and but this one is like a move instruction, so it actually copies the value at memory location to EAX register and returns. All right. So this one actually concludes this like a lecture. So I explained like arrays and structures, how these arrays are represented, and how we can access specific element within the array, like a one-dimensional and two-dimensional arrays. And structures, we also covered how those like elements are packed into single like a region of memory, and also talked about array of a struct and so on, and also talked about alignment, so all these things. Right? Questions or comments? Okay, let's move on to chapter 4. So here, so now we are moving on to chapter 4, and the first part is why x86-64 ISA. So what the heck is y86-64? Because we already covered x86-64, and what is y86-64? So this is basically the toy. This one is a toy ISA. Very small, like a stripped down version of x86-64 for like educational purpose. Because the idea is, because now we're going to move on to the hardware side, because we already learned like a software assembly language, we already learned the language of computer, which is assembly, right? Then the next like topic is how we can make the hardware, that actually logic, that can efficiently execute this like a set of instructions, right? That's what we want to cover. But the original x86-64 is too complex, too many instructions, too many types. So we actually come up with like a small subset of instructions, and we're gonna make a processor that can execute those like a small subset of instructions. Okay, so that's the like toy ISA we want to make hardware for. And so let's think about what's the role of ISA, instruction set architecture. So ISA is actually placed here. So this one is actually placed in the boundary between software and hardware. This one is software, this is hardware. So ISA is kind of the place in the middle between software and hardware. So from like a software point of view, like assembly language view, by the way, these ISA actually provide like abstraction for CPU, like processor. So it actually defines the processor state. So what kind of states are there, like such as like registers, how many registers are there, what's the like a memory, like alignment requirements. That's a kind of part of the ISA definition, how this alignment must work. And registers, memory, and flags, like conditional code, all these things, they constitute the processor state. The state as in the meaning of FSM, finite state machine, like a state, right? You program state. And instructions, it also defines like instructions like add queue, sub queue, like push queue, ret, call, all these things. ISA, defines those set of instructions. And also it defines how those instructions are encoded as byte, right? So in order for processor to execute those like instructions, it eventually must be encoded into ones and zeros, right? 1, 1, 1, 0, 0, something like that. So ISA also defines how individual instructions will be encoded as a string of ones and zeros. Okay, it's like a assembly language view. And as I said, ISA is placed like in the middle of hardware and software. And above ISA, there are like compilers and operating systems. Those are called like a system software. This is called like application software, right? So above, this one actually serves a layer of abstractions, because ISA, then you can actually program this processor and write assembly code for this processor, and this CPU will execute those like instructions. So processor executes those instructions in sequence. So any like a piece of software will be eventually translated into a set of instructions. And below ISA, This one is actually specifies what needs to be built. Okay, so if you actually divide, let's say you have like a CPU, like any let me make an analogy. So make an analogy. So if you actually have, if you write program, you usually have like a header file and like implementation file. So let's say you actually have something like hello.h header file, and it actually also has like a hello.c, which actually implements the function. So this one only provides the interface. This one only defines function signature. So let's say how many arguments must be passed to the function, and what's the return type. That's called function signature, right? So it only defines the interface. What's the input? What will be the output, right? That's defined in this header file. And this hello.c actually implements that function. So it actually has a content. So what needs to be executed to realize that input-output behavior, right? So this kind of analogy, you already know the analogy. The separating of interface from implementation. So this one's an interface. This one is like implementation. So what if we apply the same idea, like separating interface from implementation to the CPU design? Okay, then this part is more of the implementation part. Implementation, and this ISA serves as interface to the software. Okay, so once you actually fix the ISA, your hardware must implement that like interface, that like those like operations, instructions, right? But there are a lot of like freedom, how you realize those like implementation, because maybe this underlying CPU can run in like 3 gigahertz, maybe run in like a 4 gigahertz or 2 gigahertz. It's kind of implementation detail. Also, maybe you can execute just 1 instruction at a time, or you can execute like 2 instructions at a time, or 4 instructions at a time. That's also kind of choice of implementation. But they actually do the exactly the same thing, in the sense that once you actually have your program written in like machine code assembly, then CPU must generate the output as if it execute single instruction one at a time, like a one by one, sequentially. If the output is the same, then it doesn't really matter how you do it. Maybe you can do it like actually really do it in order, like of the original program order, or you could do some like out of order execution, maybe like a later instruction, you execute later instruction first, but you can still preserve the overall behavior of the program, then it's fine. So all of these things are kind of issue of implementation, like designing the CPU. So this ISA actually serves as the interface to the software, and then the hardware is kind of implementation of the software interface. So that's basically the role of ISA for hardware. So as I said, y86-64 is a stripped down version of x86 64. Okay, like a small subset of the instruction set. And actually, we're going to make hardware that can execute these like a subset. They can execute like these instructions. So here, let's define the processor state first. So we actually have like 15 program registers instead of 16. We are missing like 1 register, but we actually have like 15 registers instead of 16. There's the program registers, and each register actually has 64 bits, and we actually have 3 conditional codes: 0, like assigned, and overflow. But there's no carry. There's no carry flag, so we only have like 3 conditional code, and also program counter or instruction pointer, the same thing, right? The PC actually points to the next instruction to execute, right? The pointer to the instruction. So program counter. And also program state, like a program status register. So program status register actually indicates either everything is running okay, or you actually enter into some special like error state. Maybe let's say you try to execute some instruction that's not defined, then maybe it's kind of erroneous situation, right? Then that is actually placed. That information is actually placed in this like a status program status register. And also we actually have memory. So memory actually is byte addressable storage array, and words stored in little endian byte order, because it's basically derived from x86-64, which is little endian architecture. That's like a program state. And now we define instructions, because now we define the state. If you execute like an instruction, that actually access your system's state, like a CPU state, and move it to the next state, if you, as a result of execution, right? So we actually defined how many, like 1, 2, 3, 4, like 10, it was a little bit more than like 10 instructions for this ISA. The first one is a halt, NOP, like a conditional move, IR move. IR move is immediate to register move. So this one is like a conditional move, which takes like two registers. RA and RB are registers. So this one is a conditional move, copying the value from RA, register A to register B, if this XX condition is satisfied. XX could be like LE or GE or G or something like that, right? You know that conditional move. The second move is IR. IR is like I'm going to explain one by one more later, but it's like a move instruction is from IR move is immediate value, copy immediate value to register. RM move actually copies register value to memory. RM is like a register to memory, and MR is memory to register. And OPQ is like something like add, sub, mar, all these things, right? So it's basically arithmetic operations. It takes two registers as input, and it actually what it does is it calculates the value of RA, some operation RB, and store the result back to the RB. And then op could be add, sub, or something like that. There can be like multiple, it's actually determined by this field, like F field. And jump instruction, call instruction, return instruction, push and pop. That's kind of subset instruction we want to implement in our hardware. So here's the format. So I'm going to go over one by one more details, so don't worry too much about it. So here's the format. It takes like 1 to 10 bytes of information read from memory, because in this case, for example, this halt instruction only takes like 1 byte, right? And no instruction, like a no operation, it takes like 1 byte too. And in this case, this one actually takes 2 bytes, because it actually takes 1 byte for opcode, what kind of operation it is, followed by 2 register specifier, because we need like 2 registers here, like RA and RB, and each register, to specify one register, it takes 4 bits, right? Because we have like 15 registers, we actually have to have at least like 4 bits to specify the register name, right? Because we have 15 registers, right? So actually, the first 4 bytes actually specify RA register, and second one actually specify RB register. And this one is really a long instruction, because this one, immediate to register copy, move. So in this case, we actually have to have some like constant value, like 8-byte constant value V is placed here, and then this RB is the destination register. This F is fixed value, like a fixed value 1111, which means like a no register. But that's basically why we actually need this one actually takes like 10 bytes for this instruction, and so on. So minimum width is 1, maximum width is 10. Okay, depending on what kind of operands this instruction needs, right? So 1 to 10 bytes of information read from memory, and can determine instruction length from the first byte. Because if you actually fetch this byte, the first byte, then we know that we can actually decode. It's called decoding. Once you actually read the first byte, we know that what kind of instruction it is, right? So once you read the first byte, you can determine how long this instruction will be. And not as many instruction types as original x86-64, and simpler encoding than x86-64. And each access and each instruction actually accesses and modifies some of the program state, which is defined like 2 slides ago. So halt, I already explained halt and NOP. Halt is basically you stop your program and do nothing. It's like you're halt. You're done. you do nothing. You just stop there, stop your program there. And NOP is basically no operation. You just do nothing and move to the next instruction. That's NOP, no operation. And the third one, this is conditional move. There's like a suffix XX here. So in this case, you know, in this case, CMove, if you remember, CMove is executed only if this condition is satisfied, XX is satisfied, right? So in this case, you know, it takes two registers, RA and RB, and copy the value of RA to RB if this condition is satisfied. And this condition is specified in the second, like, nibble. Nibble is like a 4 bits. The second, this part actually specifies the condition. So if it's unconditional, meaning that if it will be executed without, you know, it will be always executed, then this like condition code will be 0. If it's 1, it's like LE. If it's 2, it's L. 3, E. 4, NE. 5, GE. 6, G. So if you actually read like these two values, these two like nibbles, like a 4-byte block, actually you exactly know that what instruction it is, depending on the value of the second nibble. This one, a nibble. It's like a 4 bits. It's like a smaller than byte. And so this one is easy, like IR move, the instruction to register move, you copy the immediate value to register. RM move is you copy the register value to memory, but we only support this format, like displaced access, D and register, instead of like a fully developed this scaled access. We don't support that in this case because it's too complex to implement. So we only support like a very simple like memory addressing, register value followed by constant like displacement. And this is MR move, the opposite direction. This is, by the way, this is called store instruction because we copy the value of register to memory. This is called store. And what is this called? The opposite of a store. Copying value from memory to register is called load, right? Load and store. And this OPQ is like an arithmetic operation, which is, depending on the value of, depending on the value of this FN field, like a nibble, it's either add, sub, AND, or XOR. So let's say if the first byte is 60, then it's like add instruction. If it's 61, then it'll be sub instruction. If it's 62, then AND instruction. 63, then it'll be XOR instruction. Okay? The next one is jump instruction. This is unconditional jump. Unconditional. And the next ones will be this one will be conditional jumps. Depending on the flags, depending on the value of flag, it will be either jump to the target or otherwise just go to the next instruction, right? It's like a conditional. And this one is the encoding of this like a variety of this jump and branch instruction, unconditional and conditional jumps. Call instruction, return, you already know what they are, and push and Q, you already know what they are. And this like F thing is basically constant F. Constant is basically no, constant F as register specifier is basically no register. So because in this case, in push and pop, we only need like a one register specifier, push and pop, right? So the second like a register specifier is simply marked as F. F is basically no register. Because we actually have like a 15 register like this. You see here, we have like a 15 registers, and 0 through like a E actually maps to real like register. Like a 0 is RAX, 1 is RCX, 2 is RDX, 3 is RBX, and so on. And the last one, like F, the 1111, means no register. It's like empty. And this is the same encoding as in original x86-64. And we're going to use register ID 15 to indicate no register. So it's actually used here as an example, like this one, like push and pop, because push and pop needs just one, as I said, register, but there's like another field. So in this case, we use like F to specify we don't really need second register in this instruction. So let's take a look at more concrete like examples of instructions like add. So here's the addition instruction like add. It actually takes two register operands, RA and RB, and it's encoded as 60 followed by two register specifiers, RA and RB. So it's like a 2-byte instruction. So what it does is add the value of register A to that of register B and store the result back to register B. Okay, this is no surprise. And condition codes are set based on the result of computation. Right? If there's an overflow, then the overflow bit will be set. If the value become minus, then the sign bit will be set, and so on. Right? So if you actually write the code, something like add q RAX RSI, then this one is RAX is RA, this RSI is RB, according to this format. So we're going to actually put this register specifier for RAX and RSI to these two fields. So if you go back to the previous slide, RAX actually has the register specifier of 0. RSI actually has a register specifier of 6. So we actually place these two value, 0 and 6 here. Then that means like a 6006 in machine code translates to add q RAX RSI. This one actually translated to machine code, and this machine code can be translated to assembly like this. They are the same thing. So we actually use 2-byte encoding. The first byte indicates instruction type, in this case add q. 60 means like add q. And second gives source and destination register specifiers. This is, we generalize it, arithmetic, logical operations. So add instruction is 60 RARB, subtract sub q RARB. Actually, this one is actually wrong. This is subtracting RB from RA. The end is 62 RARB, exclusive OR RARB. So always the RB is the target register, the destination register. They actually have the exactly same format. So this one is function code, and this one is instruction code. So instruction 6 means like some like arithmetic. Oh, by the way, time is up. Sorry, I just passed. All right, so I'm going to stop here. I'm going to continue next time.